Good morning. We are moving on. It's another chapter, another day, another chapter. And this is kind of a big step for us. Chapter 21, 22, 23. We have been looking at electric forces, electric fields, electric potential energy, electric potential. And now what we want to do is kind of switch gears and start looking at circuits. So the way this part of the course works is we just spent 3 weeks looking at electric fields. Now we're going to spend a couple weeks looking at circuits, and then we'll come back and look at magnetic fields for 2 or 3 weeks, and then we'll look at some more circuits. Right now we're going to be looking primarily at DC circuits, and then we'll move on to AC circuits. Now this chapter, chapter 24, we were looking at devices that are called capacitors. And capacitors store charge. Now they've got all this stuff going on in the title. I think the dielectrics, that's not such a big deal. That's a small item at the end of the chapter. But the chapter primarily is about capacitance, which refers to devices that can store charges. Now these devices here, they're all what we call capacitors. You'll notice they have a couple of wires attached to them. We can connect that to some kind of a voltage source, a battery, for example, and we can store charge in these devices, which becomes really handy, as you might imagine. So let's get started here, although I do have to kind of stare at these different components. It used to be, it's not so much anymore, it used to be you could take everything apart, right? You could open up your TV set, you could open up your stereo, and you would see all these components inside. That's a variable capacitor right there. That used to be in one of those in my stereo system back in college and grad school. Anyway, let's move on here. So here are the items, here are the topics we're going to be looking at. Here is a capacitor. So even though those devices were all funny, different shapes, I don't want to say they were funny, but they were different shapes. What they all come down to, more or less, is 2 layers of conducting material. But the conducting material, the 2 conducting pieces, are held apart from each other. They're put really close to each other, but they don't touch. And so we leave enough of a gap, this distance d right here, that these devices, the charges, are not able to cross from one plate to the other, at least at operating voltages. The voltages that these devices are designed for, charges are not going to be able to go from one side to the other. So here's a couple wires, those gray things connected. See how it looks when it's rolled up? So you can imagine, once we get these sheets layered together, you can kind of put these into almost any shape that you want, like the layered example over here that's kind of like a cylinder now of the different layers. So we got these wires attached to, say, a battery, for example. And from that, what we're going to do is we're going to build up charges. Now, here's a plus charge on this side, a minus charge on the other side. So the charges in general are going to be equal magnitude, opposite sign. We've seen this kind of stuff before. And then as far as the dimensions of the capacitor device, we want to know how much of a gap we have between the 2 conducting materials. And then we want to have a surface area in order to figure out how much charge we are going to be able to store. So that's kind of our basic picture. All right, here it is, capacitor. It's hooked up to a battery. So here's a battery, and it's 12 volts, and we've dealt with voltage in kind of an abstract way. Electric potential is what we've been calling it, but hey, now it's just voltage, right? What's the voltage on that battery? So the electric potential for this battery, or what the battery is maintaining, is 12 volts. And it's doing that through a chemical reaction. So most car batteries are running reactions with lead sulfate, sulfuric acid with lead plates. So it's a series of chemical reactions with the lead, and that's an easily rechargeable battery. And it's maintained here at 12 volts. We're going to connect those wires to those plates, and hey, we end up with positive plate here and a negative plate here. Now you can think of that in terms of how we've moved electrons around. right? We said with these common electronic devices or these common electrical devices, it really comes down to, what's happening with the electrons? Well, the electrons are being pumped in the battery as a result of the chemical reaction. So that's basically what a battery does. It runs some sort of chemical reaction, and in the process, it depletes electrons at one of the terminals, and when electrons go missing, those regions become positive. And then those electrons are transferred into a negative terminal. So the battery is just pumping these things. The battery doesn't store charge. Even though we say we have a positive and a negative terminal, that just refers to the direction that the electrons are being pulled. So it really requires us to connect some wires. So we're going to connect some wires onto this, and at the negative terminal, we're going to have electrons being pushed away from there. And then at the positive terminal, we're going to have forces that are pushing the electrons in towards the positive terminal. All right, so this is what it looks like. There are the plates and the batteries. This is what it looks like in the circuit diagram. So in a circuit diagram, it's going to show the battery as a pair of plates. One of those plates is always shown as being a little bigger, a little wider than the other, and that's designated as the positive plate. And then the other side is the negative. And then, hey, the basic property of a battery is its voltage. That's it, right? When you look for a battery, you're looking for something that provides a certain voltage. So that's its property. Now, this is the symbol for the capacitor, and you're thinking, wait a minute, we just started out with circuits. We've defined two things, batteries and capacitors. They both have the same symbol. And you go, well, in the capacitor, the two plates are shown as having the same length to them. In the battery, they're not. Okay. And in the battery one here, they put the plus minus on there. That won't always be there, but you can always look for which plate is wider. So that's it. This is kind of a diagram of what it's built from, what it looks like. That's a diagram that we would use just to write down the circuit that we're describing. Now, this is what's called a parallel plate capacitor connected to a battery. And parallel plate is kind of the simplest geometry that we might imagine for a capacitor, because what that allows us to do is just have a couple layers of conducting material. Now, typically, we put something between those plates, some kind of insulator, but the insulating layer tends to be very thin. If we can keep the insulating layer very thin, but preventing conduction of electrons from one side to the other, we find out we get more capacitance. All right, here's one more diagram, very same thing here. So there's the battery. Here are all the wires. I always want, one of the things that I think is important to get a feel for what are the electrons doing in the wires. And I think often there's kind of this racetrack approach to electrons, thinking, this wire is just like the fast lane and the electrons just zip by as fast as they can. That's typically not true. So electrons are probably best thought of as forming a non-compressible fluid. So what happens is this. Even before we close the switch on a circuit and charge this capacitor, electrons are everywhere. And the electrons are kind of bumped up against other electrons. So you could kind of think of them as a bunch of blocks, a bunch of electron blocks. And if I push on one electron, it immediately repels all the other electrons. So I can't really push on one electron without having all the other electrons experience some kind of force. So what the battery provides is that force. All the electrons are lined up through the circuit, and when the battery starts pushing on the electrons, it draws electrons in from this plate, and it places electrons on this other plate. But notice, which electrons are going to end up on that plate? Are they coming from the battery? Not necessarily. There's already electrons at every location in the wiring, and that means when we turn this circuit on, electrons that were already nearby the plate are going to be the first ones to jump on and start to build up charge. Electrons are going to jump off of this positive plate into the wire, and they probably are going to be moving pretty slowly. We can actually, in another chapter, actually, chapter 25, we'll take a look at speeds. How fast are the electrons moving in a circuit? And for most circuits that we work with, the electrons are going really slow. It's not that they're going super fast through the circuit. It's that there's a bunch of them all lined up, and they behave like this closed system of blocks, where if I push on one part of the blocks, they all push on each other. It's like a non-compressible fluid. Okay, so the circuit's filled with electrons to start with. We start pushing on some of them at one location, and the electrons all through the circuit end up having to move as a result. So let's be clear too, a battery is going to pump charge. We've mentioned that a couple times now. And capacitors are going to store charge. So it's these plates on the capacitor that are able to accumulate an appreciable amount of charge. Now, there could be, tiny, tiny charges that accumulate in the wires themselves, but at least for, the 0th order approximation, those are insignificant. So the rules for right now are the battery pumps the charge, the capacitors store. Nowhere in the wiring do we get an accumulation of electrons. Now, last item with this picture, with this conceptual picture we're trying to build, you might think, well, if there's electrons everywhere, those wires are negatively charged, but that's not true, because throughout the wires, there are also protons. We're not showing the protons because the protons aren't mobile. The protons are kind of locked into place in these materials. So since it's just the electrons that are moving, that's what we've identified in the wiring. But if I look at the wires, every location, every section of wire that I look at, the electron number and the proton number balance. So there's no net charge buildup. The only place we are seeing the charge buildup is on the capacitor plates. All right. Important to think in those terms every time we look at these circuits. All right, here it is. Here is the definition of capacitance. So when we take a capacitor and connect it to a battery, we find that the amount of charge is proportional to the voltage source. So Q is proportional to V. If I double the voltage, I'm going to end up with twice as much charge on those plates. And so C, we define the capacitance as the proportionality constant. So C tells us, for a certain amount of voltage, how much charge am I going to be able to store. Now, going back to the picture here, maybe going back to the picture here, I didn't write my Q's in here, I left out the Q's. When we talk about Q, you might say, well, which Q are we talking about? The Q on the positive plate or the Q on the negative plate? And the answer is yes. They acquire the same amount of charge. So Q, when we put Q into equations, and we're going to do that a lot with these capacitors, that Q that we calculate refers to the amount of positive charge on one plate, and it refers to the amount of negative charge on the other plate. Sometimes it's easy to get confused and think, well, is it the charge on both plates? Well, it's not the charge combined, because the net charge, if we add together both plates, is 0. So Q is the amount of charge on each one of the plates. One plate becomes positive, and one becomes negative. Now, we need a unit for capacitance. We have a unit for charge. Charge is measured in coulombs. Electric potential is measured in volts. And so capacitance is measured in farads, I guess named after Michael Faraday, who did most of these. Let's see, Coulomb was a researcher in electric forces, and Volta was a researcher. They're all named after kind of the prominent people who discovered many of these different type devices. And so anyway, we're going to call this the farad. A farad is 1 coulomb per volt. And that's what the equation is going to look like. And it's got a yellow thing around it. It's got a little yellow box that it's in. Because that's an equation we're going to come back to over and over and over. All right. What determines how much capacitance a capacitor will have? And we're going to we're going to look at a number of geometries. But we're going to start with the parallel plate geometry. And what we have is this is a side view. So when they talk about the area of the plates, you know, these plates are positioned this way. And so this has a surface area, this has a surface area. There are E field lines running from one plate to the other. And there's a distance. Now, the distance here is from surface to surface. And that's because for a conductor, all of the excess charge on the conductor is going to end up at the surface. There's no E field inside conductors. Everything's going to end up at the surface. So D is really the distance between the plates, and it's the distance of the electric field extension. Once I get past the surface, there's no E field inside the plates. Now, they're using some formulas with this epsilon naught, so I put some arrows there to just remind everybody. There's kind of two different force constants that we could be using. The textbook primarily at this point has switched over to epsilon naught. I'm going to keep using little k, and then we'll be able to make comparisons as we go along. I feel like it's probably important for you to be familiar with how these formulas look using either one of those two force constants. All right. So if we know the electric field, and for a parallel plate we're assuming the electric field is uniform, then we can calculate the electric potential between the two plates. We can just multiply by D. So now here's the very same drawing, very same definition. I'm going to go back and I'm going to go back to Gauss's law. It turns out that solving for the capacitance of these capacitors allows us a chance to go back and, for better or worse, it allows us a chance to go back and look at Gauss's law. So what do you guys think? Was that pretty traumatic? Are you ready to go back and do Gauss's law again? So if I have parallel plates, if you remember, here's Gauss's law. The Gaussian surface that we defined for that, what surrounded one of the plates, not both plates, because that didn't give us any useful information. We define a Gaussian surface that encloses one of the plates, and then we can measure the electric flux passing through that Gaussian surface. Since there's just one area through which the electric field passes, the integration of the electric flux gives us E times A. Now that's going to be equal to 4 pi k q, or 1 over epsilon naught times q. So again, the textbook is taking this approach. I'm going to take this approach. And carrying through the calculation, we get an electric field within the plates given by 4 pi k q over area, or 1 over epsilon naught q over area. Now, we saw back in chapter 21 and in chapter 22, this is only a good approximation if the distance between the two plates is really small. If it's not, this no longer becomes a good approximation. So that's kind of a built-in assumption here, is that D, distance between these, is really small. So once we get the electric field in terms of the charge, and that comes from Gauss's law. Now we're gonna try some different geometries, but it's going to be the same sorts of steps. The potential from one side to the other is going to be E times D if the electric field is constant. And so we can just make that substitution. We can take the electric field that we calculated, 4 pi k q over A, multiply it by D, and now what we have is we have a formula for V in terms of Q. We have a formula that tells us what the electric potential will be as a function of how much charge is on the plates. Now, that says we can flip that formula around using our algebra skills, and say Q is equal to a bunch of constants times V, and you go, wait a minute, that's how capacitance was defined. Whatever all this stuff is in front of the V, whatever it's getting multiplied by, that's the capacitance formula for the parallel plate geometry. So I can write it as the capacitance for a parallel plate capacitor is 1 over 4 pi k. Now k is the electric force constant, 8.99 10 to the 9. And I I can't do much about that. But what I can do when I'm designing a capacitor is I have control over how much surface area does the capacitor have and what's the gap. So this is suggesting that if I want to make capacitors that have a reasonable amount of capacitance to them, I want to keep D really, really small. I want to get A really, really large. And if I do that, I'm going to meet the requirements for using Gauss's law in the first place. So that's going to tell me how much capacitance we have. Now I wrote in the version with epsilon naught, just side-by-side comparison, so you guys can follow this. All right, questions on that? Remember, capacitors are your friends. Oh no, not a problem. So we're going to come in and calculate how much capacitance there is in a parallel plate geometry capacitor. The plates are 20 centimeters, by 3. Uh-oh, I think I did this wrong. Well, not wrong. I think I misread the numbers going in. I think I did 20 centimeters by 30. Doesn't that look like a 30? Anyway, I may end up changing the numbers here. And then it says that there's a 1 millimeter air gap. Now, 1 millimeter between the plates may sound like not very much, but it turns out that's a pretty large gap. 20 centimeters sounds big. So 20 centimeters is like this. And in that first picture we looked at, I didn't see any capacitors that had 20 centimeter by 3 centimeter, unless it was all wrapped up into kind of that cylinder shape that we saw, and it could be. What is the charge on each plate? We're going to connect it to a 12-volt battery. How much electric field? Okay, estimate the area. So we got a lot of stuff that we're supposed to do here. Let's get started. So, okay, here is the capacitor. There's its cross-sectional. Oh, I did see 20 centimeters by 30. Sorry about that. But I think it'll make it it's going to work. I think that's what they intended anyway. 30 by, no, anyway. So I ended up with 600 square centimeters, and then I converted it to square meters. And then I took my D and converted that to meters because I want everything in standard units. This is all brand new to me. I'm just starting out learning about capacitors. And so I put in the 104 pi, there is K, little k, electric constant. No one's using Boltzmann's constant for little k at this point, right? That was so far in the past, back when we were doing thermodynamics. That was so far into the past. So now we've moved on, we're doing electric forces. And then I put in the area, and I put in the D, and I plugged it all into that formula, and I calculated it, and it was very disappointing. All I got was 531 10 to the minus 12 farads. Now, 10 to the minus 12 prefix is called pico. And when we design capacitors, almost all the capacitors you come across are either going to be in the micro, or the nano, or in this case, in the pico. And that's because coulombs are actually a good amount of charge. And so in these little tiny capacitor devices inside our, our TV sets and stereo equipment, we're really not storing very much charge. So that's just to be expected. If we went back now and redefined the coulomb, maybe we would. Coulombs are such big units, but anyway, it's fine. So 531 picofarads. Now, one thing I want to mention here is we're going to be doing a lot of these problems that have micros and millas and nanos and picos. Learn your prefixes. So we do not write things. We tend not to write things in scientific notation. Instead, we use the prefixes. And the prefixes that we use are the factor of 1,000 prefixes. We specifically use 10 to the minus 3, 10 to the minus 6, 10 to the minus 9, 10 to the minus 12, 10 to the minus 15, which is femto. Those are the prefixes that we use. So practice that. I don't know how your calculators work. My calculator, which is an engineering calculator designed, back in 1981, actually has what's called engineering mode, where it automatically puts things in powers of, like this, thousands. Anyway, for what it's worth. So let's see, the farad is a coulomb per volt. I just wanted to check units on this. to see if we can figure out this formula right here. So a farad is a coulomb per volt. A volt is a joule per coulomb. That gives me a farad is a coulomb squared per joule. So a farad is the same thing as coulomb squared per Newton per meter. And so those are all different versions of what farads are. And oh, that's what I knew I was doing this for a reason. I'm looking at this calculation right here. That's the one I was looking for. So yeah, I was looking up here and going, are my units all working? Because meter squared cancels meter squared. I got a meters and a Newton. Now the meters and Newton could be combined or left as separate. I got coulomb squared in the denominator of a denominator. That's going to bring it to the top. So if I look at the units that are left over there, they are coulomb squared over Newtons times meters. And it turns out that's a farad. Okay. So the units get more complicated. We've got a fairly good sized list of things we're going to define. And it gets harder and harder to practice units conversions. So practice that. Always spend a little time looking at the units, because the units, once you're familiar with them, will help guide you through a problem. So it's good to know how to get from units, but don't panic. If you can't get the units to work out, say on a midterm or something, do what you can. But anyway, practice units. There was more on the problem. That's right. I almost forgot. I was so excited about calculating the capacitance, I almost forgot we had other things to calculate. So I calculated the capacitance. Now they told me that the battery was 12 volts. That was given. And so what I could do now is I can calculate the charge. They wanted me to calculate the charge. Okay, you guys see anything? Oh no! Do you guys see any problem with my capacitor? Somebody put positive charges on both sides. One of those should be negative. So pick one of those and cross out the plus signs and put in some minus signs. Let's see. Q is equal to C times V. So that turned out to be 6.37 nano coulombs. And then to calculate the electric field between the plates, V over D will do. And that was 12,000 newtons per coulomb. All right. So I think we got everything calculated here that they asked. Now that last item though, part C, said, how big would the plates need to be? How much area would I need if I wanted 1 farad? So way up there in the corner it says capacitance is 1 farad. And what I did is I went in and solved for the area that would be needed. Now the area I got, given that we stay with the 1 millimeter gap, the area I would need is 1.13 10 to the 8th square meters. I thought 10 to the 8th square meters, that sounds like a lot of square meters. What if I imagine this being a square? What would the length of a side be? And that would be the square root, which would be 10,000 meters. This capacitor would need a surface that's 10 kilometers by 10 kilometers in order to have 1 farad. So you're thinking, 1 farad capacitors are like impossible, right? But that's not true. There are other devices that are more complicated that are able to, like this is saying right here, there are capacitors that have a complete farad of capacitance, but they're not parallel plate. They make use of different material properties in order to store a lot of charge. So kind of condensed matter, solid state properties to be able to store more charge in them. Okay, you guys ready for every shaped capacitor you could possibly imagine? Now again, what we're doing with this, you really could build capacitors like this, and devices that have this geometry to them will always have a little bit of capacitance. So let's say that we have 2 conductors. There's a central conductor here, there's an outer conductor, and that looks kind of like a coax cable. That's a common way that when we have electric wiring, coax cables have a lot of symmetry to them, and they eliminate a lot of crosstalk between the two conductors. But there's going to be a little bit of capacitance in a coax cable. And so we're asking, well, how much capacitance would there be in a coaxial cylindrical shell of these two conducting materials? Now, okay, this is another thing that really threw me off in this diagram. So you can see these little things really upset me when I'm trying to solve a problem. They have two radiuses. They called one radius A and one radius B, which I was fine with, but A is bigger than B. That's not right, is it? If you have two radiuses, shouldn't B always be the larger one? Anyway, I'm going to switch. So I'm going to switch and use B for the outer radius and A for the inner radius, just to let you guys know, just give you a heads up. Now they're saying the inner conductor has acquired a charge of plus Q, the outer conductor negative Q. And again, the picture looks like that first one, that really nice cylinder that they've drawn. So there's a certain length that we're considering. It may extend farther and farther, but we're just going to look at capacitance within a certain length of this cylindrical coax cable. I think that's everything. I think it's time to bring out Gauss's law. We're going to use Gauss's law to come in and calculate the electric field. And then we're going to use, well, we got to use Gauss's law, and then we got to calculate the voltage by integrating the electric field, and then solve for the capacitance. Those were the three steps. Let's see if we can do it. Maybe we can, maybe we can't. So here's this inner radius, and you guys may see from my notes here, I started off following their approach, and then I found out I was getting confused. Notation sometimes, it's easy to get very particular with notation. Anyway, inner radius is A, outer radius is B. Positive charge inside, negative charge outside. Here's my inner and outer radius. Now there's a variable R that takes us within the region between the two plates, and that's where the electric field is going to be. The electric field is only going to be within those two conductors, that region of space. So here's Gauss's law, and if you remember Gauss's law for a cylindrical geometry, when we integrate the left side, the E field is uniform at any one of those Gaussian surfaces that we define. So I don't know if you can see the variable R right there, but R could be represent a Gaussian surface anywhere between the inner and outer radiuses, anywhere between A and B. So that's my variable R, and the surface area of that cylinder is 2 pi r L squared. We're not including the endpoints. So the ends of a cylinder are a couple of circles. We're not including those, and that's because the E field is not directed across those surfaces. All right. So when we carry out Gauss's law, which we did, and then we solve for the electric field, we get 2kq over L, 1 over R. That may actually look familiar from chapter 22, maybe, maybe not. But that's the formula we got. So the E field starts off at some value at the inner radius, at A, and then the E field drops off. It's not as large. It's not a constant E field in this example. The E field is going to vary. Now that says that, so first step was use Gauss's law to get the E field as a function of position. Second step, calculate the electric potential from one surface to the other. By the time we've integrated that electric field, we will now have a formula that tells us about the voltage between the two plates. Inner plate to outer plate. So I did that. I integrated this, and I ended up with 2kq over L, logarithm, natural logarithm, because I had a dr over r, b over a. So first step, Gauss's law. Second step, take the E field, integrate it to get a voltage. And then final step is take a look at my formula. V is proportional to Q. as advertised. Early in those early notes, it always said that the amount of charge we get will be proportional to the voltage for any capacitor. And solving this for Q, I got Q is equal to L over 2K, ln V over A times voltage. The stuff in the brackets, that's my capacitance for a cylindrical geometry, for a coax cable. Now, what does it depend on? Well, capacitance is proportional to the length. So you go, that makes sense. If I have a cable and it's twice as long, it's storing twice as much charge. If that cable goes on and on and on and on, each section of the cable is storing a certain amount of charge. The electric force constant always shows up in the denominator, and there it is. Now the units on a capacitance, if we go back, let's see, remember the parallel? There we go. Remember the units here, maybe that's not it. The units here, for the parallel plate, there were meters squared over meters. Now, in this case, one of those meters canceled, and we're trying to get farads, right? And so we're expecting we'll have a factor of meters. No, that's not the best way to think about it, is it? I guess we want to go back to... No, I guess that is how we do it. So it's the same idea. What we'll have is we'll have a K in the denominator. We'll have 2 powers of length over 1. So I need a unit of length. And there it is. So there's a unit of length on top. There's a little k below. And then the logarithm ratio doesn't have any units. So that capacitance does have the right units. Again, there's always going to be a factor of little k in the denominator. And then there needs to be a length of some sort left over on top. So it seems like it makes sense. Okay, now you guys are thinking, wait, we're doing the same problem again? It's another cylinder, but this is clearly a sphere, right? And you're realizing that, hey, spheres and cylinders look the very same when we draw them in these diagrams, so you got to be careful. So this is actually 2 spherical conductors, one nested inside the other one. It's still plus Q and minus Q. The E field is not constant, right? The parallel plate case is starting to look pretty good because the E field was constant. The cylinder wasn't constant. The sphere, it's not constant. But here are the concentric spherical conducting shells. Now, again, they're calling it R sub A, R sub B. You know, I think they use the very same picture, even though it's a sphere this time. Yeah, I guess no surprises. Everything's the same except it's a sphere. All right, everything looks the same here. Gauss's law, that was our first step, so I'm using Gauss's law to find out what is, as a function of little r, inside that region. Little r extends from A, the inner radius, out to B, the outer radius. Carrying out Gauss's law, the Gaussian surfaces themselves now are going to have an area of 4 pi r squared because they're spherical surfaces. So E times 4 pi r equals 4, and look, that looks familiar, kq over r squared. And you go, oh, that's right. Spherical symmetry was exact in Gauss's law, and we always got the E field that looked just like a point charge. So kq over r squared. Now, the next step, that was step 1, get the E field using Gauss's law. Step 2, integrate from inner surface to outer surface, integrate the region within the gap of the capacitor to calculate the voltage difference between the 2 surfaces. So V is equal to E dr. That's the path we're going to follow. And that's kq over r squared dr. And I came up to here. That gives me a voltage difference between the 2 surfaces, minus kq over little r, integrated from A to B. Now, minus signs start to confuse me. I don't want to get multiple minus signs showing up in my formula, so my approach is always to try to eliminate minus signs as they show up. Minus signs tend to confuse me. I think it's true for most most people, there's always that advice, if you're going to make sign errors, make sure you make an even number. Do not make an odd number of sign errors, always make sure they're even, so that you get the right answer. Anyway, KQ over R, one way to get rid of a minus sign, which is a trick that I really like, is to take limits of integration and switch them. So instead of integrating from A to B, I'll integrate from B to A. That will change the sign. Because the voltage that I'm getting, carrying out this integration, should be giving me a positive number. If you've noticed, maybe you noticed this, I've left out a minus sign right here, and that's because I know that if I follow the electric field, the voltage is going to drop, and that's going to introduce a minus sign. So when I'm working with capacitors like this, I've actually suppressed the minus sign out front of that formula, because that's just one more minus sign to deal with. Okay. Anyway, for better or worse, that's what I have done. Now, when I carry out this integration, I'm getting KQ, 1 over A minus 1 over B. And I got a common denominator, that turned into KQB minus A over A times B. And again, what we can do is say Q. Oh my gosh, did I do this again? That is a big C. That's not a big V. That's a big C. All right. Okay, I hope these occasional errors just keep you guys on your toes, right? Again, I hope I get back and get that corrected, but if not, remember that. I'll try and make a note to go back. I do go back and through these. It seems like no matter how many times I go through and cross-check, I still, something comes up during the lecture. So I apologize for that, but I hope it's minor. So AB over B minus A, 1 over K, there's the K in the denominator. And if I look at units, I got meters squared on top, meters below, the units are going to check out. So I have units of length divided by a factor of little k, those are going to be the right units. That, though, is going to be my capacitance, not the voltage. So the capacitance. All right, so let's see what we've done here. We got a capacitance formula for parallel plates, capacitance formula for cylinders, which we said is really handy for a coax cable, and a capacitance formula for a spherical capacitor. So that's some interesting geometries. How many more should we do? Ooh, what about one more? So what this one is it's two wires side by side. So instead of a coax cable where the conductors are running within the other conductor, these are kind of side by side, although there's some distance between them. So I've got two conductors that are running, again, we're going to imagine this is pretty long. How much capacitance is there in two wires, one that's got a little bit of positive charge buildup and the other one negative? So, if I have side-by-side conductors, that also could create a little bit of capacitance in the circuits. So the wires could have an effect on each other. Now what we're assuming here is that the wires are really thin. So this time we're imagining that the wires are really thin compared with the distance between them. D is much, much greater than R. Let's take a look. We know how to do this, right? What's step one? Oh, not quite. Sorry, I had one more picture in here. So this is a dipole diagram that I borrowed from another chapter because it works well in this case. Now, in this picture, where we're looking at wires, this is not a dipole. These are two long wires that go on and on and on. But I'm just including this to see what the E fields look like, because the first step we got to carry out is we've got to come up with a formula that will tell me what the E field is at every point between these two wires. Now, if I follow this path, or one of these paths down here, any of these E field paths could be integrated and they'll give me the same voltage. but some of these paths are going to be easier to integrate than others. And so I'm going to pick that path right through here. So if I get wires charged up, there's going to be a set of equal potentials, and there's going to be a set of electric field lines. There's going to be an electric field at every location. This is not a trivial integration. So I'm going to pick the easiest path I can, and I think it's the path right through here. So again, just to get a better picture of what's going on. All right, these are not parallel plates. That's a wire, and there's going to be an E field directed between them, and the E field path we're following is the easy one. The easy one that runs directly between the two, but there are other E field paths, ones that arc upwards and come back down, ones that come out of the page, loop around and come back down. We're going to take that easy path. Again, we're going to look at just one length of wiring and call that little L. The wiring may go on and on and on forever, right? But we're going to look at a section at a time. There's going to be a voltage between the two surfaces, and here's that big R, the radius of the wiring itself. And then I went with A and A. They wanted this in terms of D, distance between the two, and that's fine. But for actually carrying out the integrations, I always feel more likely than not, the integration will be easier if I pick a point in the middle so that the wires are placed symmetrically. Usually if we have that symmetry working with us, we'll do better. Okay, so that's the plan here. And so now for this, we didn't use Gauss's law. There was an E field formula that we had, actually it was from Gauss's law, wasn't it? An E field formula that we had calculated surrounding a charged wire. So again, we're using kind of a cylindrical approach here for the E field. Now, the problem here, or the complication, is that I have at each point, as I go from the positive side over the negative side, at each point I got two contributions to the electric field. One of those is coming from the plus charge, one is from the minus. Now if I identify a point A, it turns out that both of those contributions are in the same direction. So they're going to add together. So I called the total E field along that path E plus plus E minus. The contribution from the plus wire, contribution from the minus wire. And then I wrote these as KQ over L. Now, the R, when we derived that formula, that had to do with distance from the center of the wire. And so I wrote that. If there's a point A right here, it says that the positive wire is a distance A plus X. So I wrote that distance as 1 over A plus X. Now, the negative wire is going to be a distance A minus X. So I drew the plus on the left side and I drew the minus wire on the right side so that the E field was always in the positive direction, for better or worse. I, again, try to eliminate minus signs. And so we just want to check what happens if X is negative. And if X is negative value, if we're over here, then I think we're fine, because this will get smaller than A and that one will, yeah, it's fine. So there's always this question of when we define distances, does it work all the way across the region of integration? And those two formulas do. So the E field between KQ over L, I got a common denominator, and I ended up with 2A over A squared minus X squared. So that's the E field formula. Now, you might be a little worried, I know I am. Look at that denominator. Think back to your calculus classes. When you were doing functional analysis in calculus, did A squared minus X squared in the denominator, was that a concern? And you go, absolutely. Because the concern here is, if X were to go to A, if we're going to be looking at a value of X that equals A, the denominator could go to 0. The electric field could go infinitely large. Now, anytime we have a formula like this, where the electric field goes infinitely large, or the electric potential goes infinitely large, what it really tells us is that we don't have the correct view of the object that we're thinking of. What this is really telling us is there's no such thing as a point charge. Even though we talk about point charges all the time, in reality, any charged object, once you get close enough to it, you can see that it's actually got some size. And so if I follow the electric field right up to that object, it remains finite. It doesn't go infinite. It would only go infinite if you had charge concentrated into no volume at all, a true point that has no volume. So we'll have to watch for that. So I'm going to go ahead and make a mental note that we may run into problems with that when we start to integrate from one side to the other. You guys know, again, from calculus, that sometimes when you integrate over functions that look like they might be infinite, you still get a finite value. So we'll see if that is a concern or not. So the plan then would be to calculate the potential between the two wires as integrating e dx. And what I did was I pulled everything constant out of the integral. That gave me a 2kqa over L. And I'm integrating between limits of minus a and a. So minus a and a is actually assuming the wires have no thickness. I'm just going to try that to see what happens. And then we'll adjust the limits. Because in reality, we really aren't integrating from negative a to a. We're integrating from negative a minus r. So I'm integrating from the surface, not from the center of the wiring. Okay, it's good to practice these kind of analysis of setting up integrations. So I don't know that integral, I don't have that memorized, or I don't immediately know how to go in and solve for that. So I looked in an integral table, and that's what it said. Okay, and that's fine. So I looked in an integral table, there's the integration of that. And so I carried out this integration and used this, what I found in my integral table. And then I ran it between the two limits. And I got this, I got v is equal to kq over L. Now at the upper limit, the plus a, I got the ln of a plus a over a minus a. And yeah, this is going to be a problem, because 2a over 0 is infinity, and the natural log of infinity is still infinity, so that's infinitely large. And then on the other side, it subtract the lower limit, minus a, that became 0 over 2a. Well, the logarithm of 0 is negative infinity. So it's one of those issues of, if I have infinity minus negative infinity minus a negative, that sounds like lots of infinity. So I've got infinity here plus 2 times infinity. Now, again, that doesn't mean that we have a serious problem. It just means that we can't use the limits that we had. The limits have to be written in more carefully. So I redid it. I set up the very same integration, but this time I went from minus a minus r to plus a minus r. I allowed for the wires to have a finite thickness. And once we allowed the wiring to have a finite thickness and carried out the integrations, I got this. And 2a minus r over r, that's perfectly fine, right? And r over 2a minus r, that's also going to be perfectly fine. So those turned out to be the function evaluated at those limits. And then what I was able to do, I guess, is take this and subtract this, and I ended up with the ln of this minus the ln of that. But minus the ln, I could add the ln of, so I'm going to flip that over to get rid of the minus sign, and then multiply those together. That's the same thing as getting 2 of those. And so 2kq over L, natural log 2a minus r over r. And that's it. That's the voltage. And we can relate that to Q, and the capacitance is Q over V. And so I ended up with L over 2k logarithm d over r. Now, if you notice right in here, right here, they said that the A is much, much larger than R, so I ignored the R on top and turned this into 2A, and then 2A was the same thing as what they were calling D. Okay, so that's the capacitance. So that's a lot of practice. 4 different shaped capacitors using Gauss's law, integrating the voltage. It was a great review of chapters 22 and 23. All right, we're moving on. We just have exhausted all the possible geometries we could imagine for a capacitor, maybe. And now what we want to do is look at a new topic. And this new topic is going to be really important for us. We're going to keep coming back to this every time we come back and look at circuits. And the topic is, if I combine capacitors within a circuit, what's the net effect going to be? If I were to put 3 capacitors in a circuit and combine them in what's called parallel. So it turns out that if I've got multiple capacitors in a circuit, kind of the easiest way to analyze them would be by placing them all in parallel. So if they're placed kind of side by side like this, the capacitances just add together. Now you might think, well, that makes sense because it's kind of like I got 2 plates with a certain area with capacitance, and then I add on another set of plates with more area, and I add on another set of plates. It's kind of like adding all of the areas together, and that would add all the capacitances, and that is how it works. Now, how do we know this is parallel? And it does not have to do specifically with the drawing saying that they're all lined up. There are many deceptive ways we could draw these capacitors. You actually have to stop and look at these drawings and again, stop and think about how the capacitors are connected relative to each other. So what makes this parallel is see points A and B. Well, there's a battery attached, and this battery has a certain amount of voltage, VAB, and that is going to be the voltage across capacitor 1. That's going to be the voltage across capacitor 2. That's going to be the voltage across capacitor 3. Now, when we talk about voltage across a device, that means that we get out our voltmeter. Everybody's got their voltmeters out. So to measure voltage, I put a wire on one side, I put a wire on the other side, and what we're measuring is the electric potential difference between those 2 points. So I put one contact of my voltmeter here, and I put another one here. Now if I do that, putting them on either side of C1, C2, and C3, they're all measuring the same voltage. If I have objects lined up in a way where, in my circuit, where they're all getting the same voltage, they're in parallel. All right. So, regardless of what values the C1 and C2 and C3 are. So anyway, that's what parallel looks like. Now, when we turn on the battery for these, they're all going to charge in parallel, which means that I'm going to get a certain amount of charge Q1 here, and Q2 here, and Q3 here. They're all going to have the same voltage, and so the amount of charge I get will just be the sum of all of those individual charges, Q1, Q2, and Q3. Okay, here's a little more detail about the same diagram as before, and what we're saying is because they're in parallel, each one of these capacitors will have the same voltage. So V1 is the same as V2, is the same as V3, and we're just going to call that V, which is the voltage on the battery. Now the charges are going to depend on how much capacitance we have. If C1 is bigger or C2 is smaller, they're going to have more or less charge because they're all getting the same voltage. So the voltage difference, there is no voltage difference. So it really will come down to capacitance, and that will determine how much charge we have. So let's just try this. Let's say we have a battery and it's 20 volts. We're just picking some numbers that make the calculations easy so we can see what's going on. C1, C2, and C3, let's say that those are 10, 20, and 30 microfarads. And so the charge on capacitor 1 is C1 times V, charge on capacitor 2, charge on capacitor 3, and I'm getting 200 microcoulombs, 400 microcoulombs, and 600 microcoulombs, putting the numbers into those formulas. So that's the total amount of charge we have. Now, let's say that we want to define something called equivalent capacitance. Now, equivalent capacitance for a parallel set of capacitors is defined this way. If I took these three capacitors that are in parallel and I combine them into one capacitor that would have the same voltage and the same total charge. So the V's are the same. In my equivalent capacitor, see how I only have one capacitor here? And that's the combination of all these other three capacitors. The voltage is the same, that hasn't changed, but the Q's have. So what it says is that the total amount of Q I get will be C1V, C2V, C3V, and so I can say the total charge is C1 plus C2 plus C3 times V, and that boxed formula defines my equivalent capacitance for a set of parallel capacitors. And I can have any number. If they're in parallel with each other, I can just add their capacitances together. So combined, these three capacitors have a capacitance of 60 microfarads. All right? And then I can check and say, well, what would the total charge be then if I took the net capacitance, multiply that by voltage, and it tells me if I use my equivalent capacitor, I'm going to get 1200 microcoulombs, and that's the sum of all the Q1s, Q2s, and Q3s. So it's just a check to see if we've done the calculations correctly. Okay, now parallel is the easier case for capacitors. So putting these in parallel, again, is kind of like adding the areas of the capacitors together. What if I put them in series? So the circuit we have now, here's a battery. They should have put a switch in here so we could turn this on and talk about what happens when we first turn on the circuit. If I close the switch, current's going to start moving everywhere at the same time. Now, even in these segments, see segment A and segment B, there's going to be current traveling in those segments because every time a positive charge shows up here, it's going to draw a negative charge to that plate, and that's going to create a positive charge on that plate. So these capacitors, even though the plates on the two sides, there's a gap, the flow of electrons behaves as if there's no gap. The electrons do end up going onto the plates or leaving plates, but the wiring itself, you know, if I was looking at the current of electric charge traveling through regions A and B, the currents in these regions would match the currents in other parts of the circuit. It's kind of an interesting features of capacitors. We can talk as if the current is flowing through a capacitor even though there's a break between the two plates. Okay, we got a close-up version of this one too, so let's take a look. I think it's always good to get the plus and, oh, I didn't do that, huh? Sorry, I should have added, oh, they got plus and minus here, we're fine. So you can see the way that these plates are going to get charged, which side's positive and which is negative. Now the other thing, which this diagram is going to be really useful for, is that the Q's now are all the same. So the idea is this, well, whatever charge accumulates here, there's going to be an equal amount of negative charge on the other plate. Well, if there's negative charge here, there must be positive charge on this plate, and it's got to be the same magnitude. So when we have, and so on down the line. So when we have capacitors set up in series, what it says is that I've got a continuous path that goes through some number of capacitors, and there's no junctions in between. There are no junctions in region A, there are no junctions in region B. Whatever charges are going through this region, all of the capacitors end up acquiring the same amount of charge. So there's this nice symmetry between parallel and series. In series, it's the voltages that add together. It's the charges that are all identical. So the charges are all going to be the same. Q1, Q2, Q3. We're just going to define that as Q. Now, the voltages, again, let's say we have a battery, maybe it's 30 volts or something. Those voltages, V1, V2, and V3, the total voltage from the battery is going to get divided up among the three capacitors. The voltages are going to get divided. Now, I can start from these formulas, specifically the one on the top, and for V1, V2, and V3, I can substitute in an expression in terms of Q's. All the Q's are the same. So that gives me a formula that looks like this. And then I can factor the Q's out, and the equivalent capacitance formula for capacitors in series comes from adding the inverses of the capacitance. And remember, the overall capacitance is, in this formula, this is 1 over C. Not C, but 1 over C is equal to 1 over C1, 1 over C2, 1 over C3. We can take the same three capacitors we had before. Now before, when we added these together, they added up to 60 microfarads. That wasn't so difficult. We just added the capacitances together. But this time, we're following this crazy formula. And what that tells us is the capacitance, when we're adding these in series, the overall capacitance will be lower than any of the individual capacitors. So I know that when I add them together, it's going to be less than 10, and sure enough, following through the formula, I got 5.45. Now, what we can do is we could go through as a check. We said that these voltages are supposed to add up. Let's try that. I'm taking the total capacitance of all three combined in series and creating a new circuit. We said the total capacitance 5.45 microfarads. It's a 20 volt battery, sorry, it's a 20 volt battery is what we had before. That says that the total charge overall is 109 microcoulombs. Now that 109 that we calculated, that was the charge on each, individually, each capacitor has that much charge. So when we're in series, we don't add the charges together. The value we get for the charge is the same on each capacitor, and it's just one value that we're solving for. Now I can take that charge and I can use that to calculate how much voltage do I have across each one of the capacitors. If I get out my voltmeter, everybody's got their voltmeter. Here's my electrodes, put it right there, measure voltage 1, put it right there, measure voltage 2, put it right there, measure voltage 3. Those are all going to be Q over capacitance, and I put the numbers in. The voltages turn out to be 10.9, 5.5, 3.6. The voltages are going to arrange themselves in a manner where all the charges are the same. So for the lower capacitance, where are they? The lower capacitance capacitor is going to need more volts. The medium one will need medium amount of volts, and the highest capacitance won't need as many volts to acquire the same amount of charge. And so the voltage ends up dividing up where V1 is the highest and V2 is in between and V3 is the least. Now, my check here is that all these voltages combined should add up to the voltage on the battery. All right, and they do. So it looks like it worked. Apparently it worked, we're going to say. So series and parallel, those are really important. Let's get a start here. We're going to definitely pick up next class. We're going to pick up with looking at some more of these capacitors in series and parallel. Here is a set of capacitors. I got 1, 2, 3 capacitors hooked up to a battery. And the first question here would be, all right, are these capacitors in series or are they in parallel? And the answer is it's complicated, right? It's more complicated than that. What we've got are C2 and C3 are in parallel. They're side by side. They're connected by junctions over here. There's no junctions intermediate to those. So C2 and C3 are in parallel. What about C1? Now, C1 is not in series with C2 because there's a junction right there. Well, is C1 in series with C3? No, there's a junction between that. So how do we bring C1 into this? And what we do is we do this in steps. So first of all, we're going to be combining C2 and C3 into one capacitor. Once C2 and C3, I think we got a diagram of that. Let me jump ahead here. So we're going to take C2 and C3 and bring them together. Now that was two capacitors in parallel. Now that I have this new capacitor, C23, defined, that one is in series. So I have to do this stepwise. And it's fairly involved. We'll stop right here, I think is the best thing to do. We'll come back and we'll pick up with this and take a look at these capacitors, combinations of capacitors in circuits.